Comet tails are supposed to be made of ice and dust, harmless frozen debris that sparkles in telescopes and occasionally gives us a meteor shower. But at 4 in the morning on December 26, 2025, a leaked document from the Joint Space Weather Task Force revealed that 3I Atlas didn't leave behind ice. It left behind wiring. Not dust drifting harmlessly through space, but a conductive filament threading between Earth and the Sun like a copper cable between two power terminals. We're not flying through a comet's tail anymore. We're 40% through an electrical connection that turned our planet's magnetic shield from insulator to conductor. Stay with me until the end, because what scientists discovered in that debris explains why the storm won't stop, and why we might be permanently plugged into something we can't unplug from. The story isn't over yet. Hit subscribe to stay with us as fresh data comes in, and we continue investigating whether 3I Atlas was simply passing through, or whether it fundamentally rewired something in our solar system that we're only beginning to understand. The observations keep coming, and so will our deep dives into what they mean. We're not going anywhere. The silence ended at 4 in the morning on December 26, 2025. Someone leaked an internal brief from the Joint Space Weather Task Force, and within hours, the entire narrative around 3I Atlas collapsed. Scientists weren't being careful. They were being terrified. The document used a phrase that doesn't appear in any astronomy textbook: conductive filament. Not dust trail, not icy debris, conductive filament. The kind of language you'd expect from an electrical engineering disaster report, not a comet flyby analysis. You have to understand what this means. When comets pass through the solar system, they leave behind trails of ice crystals, rock fragments, bits of frozen gas. We fly through that material all the time. It creates meteor showers. It's beautiful. It's harmless. But this brief described something fundamentally different. The debris field left by 3I Atlas wasn't scattering harmlessly into space. It was threading itself between Earth and the Sun like a copper wire between two terminals. We didn't just fly through a comet's tail. We flew into an electrical connection we never asked for and can't disconnect from. The media spent months talking about 3I Atlas like it was just another space rock with a weird orbit. They showed you the pretty pictures from Hubble. They explained how the Parker Solar Probe got close-up data. They told you it was the third interstellar object ever observed by science, discovered in July 2025 by the Atlas Survey telescopes in Chile. What they didn't tell you, because nobody knew yet, was that this object wasn't passing through our solar system. It was wiring it. 3I Atlas follows what astronomers call a hyperbolic trajectory. That means it's not in orbit around our sun. It came from somewhere else in the galaxy, swung past us at incredible speed, and will leave our solar system entirely. Except it left something behind. Something that doesn't behave like normal comet debris. Something that turned the space between Earth and our star into a circuit board. The brief described Earth's current state with clinical precision. We are approximately 40% through the debris field. The conductive properties of the material are causing sustained electromagnetic coupling between Earth's magnetosphere and the solar wind. Translation: our planet's magnetic shield isn't blocking charged particles from the sun anymore. It's conducting them. We lost our surge protector, and nobody noticed until the damage was already happening. Think about what that means for a second. Earth's magnetic field has protected life on this planet for billions of years. It's the reason solar radiation doesn't strip away our atmosphere. It's why we have an ozone layer. It's why you can walk outside without getting cooked by particle radiation from space. That protection didn't vanish. It changed function. Instead of deflecting energy, it's now channeling it. We're not shielded anymore. We're plugged in. The psychological impact of the silence after the flyby was its own kind of torture. Scientists kept saying everything looked normal. Space agencies reported nominal conditions. The sun was quiet. Earth's magnetic field showed typical variations. Everyone wanted to believe we'd dodged whatever cosmic bullet 3i Atlas represented. But that silence wasn't safety. It was latency. It was the time it takes for consequences to propagate through a system that operates on scales we barely comprehend. The storm didn't start immediately because storms don't work that way when you're dealing with electrical connections stretched across 93 million miles of space. When geomagnetic storms happen normally, they're events. They have a beginning, a peak, and an end. The sun burps out a massive cloud of charged particles. It slams into Earth's magnetosphere a few days later. We get spectacular auroras and maybe some satellite disruptions, and then it's over. The magnetosphere does its job. It deflects. It absorbs. It recovers. This time, the storm never peaked because it never had to. The energy just keeps flowing because the connection is still there. We're not experiencing an event. We're experiencing a state change. The brief mentioned something else that should make your skin crawl. Standard solar wind, the constant stream of particles our sun releases every second of every day, is now having amplified effects on Earth's electromagnetic systems. We're not even talking about solar flares or coronal mass ejections. Just the baseline radiation that's always there, the stuff our magnetosphere normally handles without breaking a sweat, is now causing measurable disruptions. It's like someone replaced the insulation around a power line with aluminum foil. The wire still works, but everything around it starts conducting electricity it shouldn't. You have to ask yourself, what kind of material could do this? What kind of debris could turn empty space into a conductor? Comet tails are mostly water ice and dust. They're insulators, if anything, but the brief's language suggests something else entirely. Something metallic. Something that responds to magnetic fields in ways that shouldn't be possible for a natural object passing through our solar system. Something that makes you wonder if 3i Atlas was ever really a comet at all. The worst part? We're only 40% through it. If the effects are this pronounced less than halfway in, what happens when we reach the densest part of the debris field? What happens when Earth is maximally connected to whatever this thing left behind? The brief didn't speculate. It just presented the data and the projections and let readers draw their own terrifying conclusions. Because when you're dealing with planetary-scale electrical phenomena that nobody has ever observed before, speculation is all you have. Speculation and the creeping certainty that we're about to find out what happens when a planet loses the one thing that kept it safe from its own star. Scientists have a beautiful model for how geomagnetic storms work. The sun releases a massive burst of charged particles during a solar flare or coronal mass ejection. Those particles travel through space at speeds up to several million miles per hour. When they reach Earth, they encounter the magnetosphere, our planet's magnetic shield that extends thousands of miles into space. The solar wind pushes against this shield, compressing it on the side facing the sun and stretching it out into a long tail on the night side. Some particles get deflected completely. Others follow magnetic field lines down toward the poles, creating auroras. Eventually, the pressure subsides, the magnetosphere rebounds, and everything returns to normal. It's a storm in the traditional sense. It comes, it batters our defenses, it leaves. The boundary where the magnetosphere meets incoming solar wind has a name, the magnetopause. This is where the physics gets interesting. When charged particles from the sun encounter Earth's magnetic field, something called magnetic reconnection can occur. Field lines from the sun's magnetic field and Earth's magnetic field can break and reconnect in new configurations, allowing some solar wind energy to penetrate the magnetosphere. But this reconnection is episodic. It happens in bursts. The field lines snap together, transfer energy, and then snap back. The key word there is snapback. The magnetosphere is elastic. It gets pushed, it deforms, and then it recovers. That elasticity is what makes geomagnetic storms temporary. The internal brief describes something that shouldn't be possible. The reconnection events aren't episodic anymore. The snapback failed. Imagine stretching a rubber band and having it stay stretched permanently. Imagine pulling on something elastic and having it just accept the new shape without any resistance. That's what appears to be happening at the magnetopause right now. The boundary between Earth's magnetic field and the solar wind hasn't collapsed, but it hasn't recovered either. It's stuck in a state of sustained connection, continuously allowing energy to flow through rather than deflecting it. They gave it a name in the brief: Sustained Connection Event. The capitalization was intentional, like they were naming a new category of phenomenon that would eventually end up in textbooks, assuming anyone survives long enough to write those textbooks. A sustained connection event describes a condition where the magnetosphere maintains structural integrity but loses functional effectiveness. The shield is still there. It's just not shielding anymore. It's conducting. This is where real-world science provides some context, even if it can't explain what's happening. NASA's Parker Solar Probe was designed to study the sun's outer atmosphere and solar wind-up close. The Advanced Composition Explorer, or ACE, sits about 1 million miles from Earth in the direction of the sun, constantly monitoring incoming solar wind. These instruments measure particle density, velocity, temperature, and magnetic field orientation. Under normal circumstances, they give us about an hour's warning before solar wind changes reach Earth. Right now, their data streams show something continuous rather than intermittent. The solar wind parameters keep fluctuating in ways that correlate with changes in Earth's magnetic field, but without the usual delay or decay patterns. It's like watching two systems that should be separated by empty space, behaving like they're physically connected. Someone in the brief's authorship chain started using the term zombie storm. Not dead, not alive, not following any conventional pattern. A geomagnetic storm that refuses to dissipate, because it's not really a storm at all. Storms are discrete events with energy budgets. They expend energy, and they end. What we're experiencing now doesn't have an energy budget. It has a connection. The sun produces energy continuously. If that energy has a direct path to Earth's magnetosphere, the storm doesn't need to end. It just persists, feeding off the sun's constant output like a parasite that found a permanent host. The implications start to cascade once you accept this premise. Earth's magnetosphere still exists, which means we're not completely unprotected. But energy is flowing through it in ways that bypass normal deflection mechanisms. Think of it like having a fence around your property that's still standing, but has hidden gates installed that you don't control. The fence looks intact. It might even stop some intruders, but others can walk right through, and you won't know they're there until you notice things missing from your house. Satellite operators started noticing anomalies weeks ago, but they attributed them to normal space weather variations. Communications satellites experiencing unexpected signal degradation. GPS systems showing intermittent accuracy issues. Even the International Space Station reported unusual particle flux readings that didn't correlate with predicted solar activity. Each incident was minor enough to explain away individually. Collectively, they paint a picture of a space environment that's fundamentally changed in ways our monitoring systems weren't designed to detect. The phrase that keeps appearing in technical discussions is "through it, not on it." Traditional geomagnetic storms happen on the magnetosphere, pressing against it from outside. This event is happening through the magnetosphere, using it as a medium rather than encountering it as a barrier. The difference sounds subtle until you realize it means every protective mechanism we've relied on for the entire history of technological civilization might be operating under compromised conditions. We built our satellites, our power grids, our communication networks, assuming the magnetosphere would do its job. We never considered what happens when it starts doing someone else's job instead. The brief included projections, And this is where the scientific language became almost poetic in its horror. If the debris field maintains its conductive properties, and Earth continues moving through it for the predicted duration, we're looking at sustained electromagnetic coupling that could last months. Not a storm that peaks and subsides. Not a series of discrete events. Just continuous, unrelenting pressure on every electromagnetic system on and around Earth. Our technology evolved in a specific electromagnetic environment. That environment is changing, and our technology can't evolve fast enough to keep up. So here's the question that should terrify you. If standard magnetic reconnection involves field lines snapping back, and ours aren't snapping back, what's holding them in place? What kind of material, drifting in interplanetary space, has the electromagnetic properties necessary to prevent a planetary magnetic field from recovering its normal configuration? And why would that material be in the debris trail of what we thought was just another icy comet from interstellar space? Physics students learn about the Lorentz force early in their education. It's the force experienced by a charged particle moving through a magnetic field. The equation is simple and elegant. Force equals charge times velocity times magnetic field strength. But buried in that simplicity is a ratio that matters enormously: charge to mass. A particle with high charge and low mass responds very differently to magnetic and electric fields than a particle with low charge and high mass. The first zips around magnetic field lines like a race car. The second plows through them like a freight train. Most of the time, this difference is academic. In space, it determines how particles interact with planetary magnetospheres and stellar magnetic fields. Now, imagine replacing the particles in that equation. Instead of the usual suspects, protons and electrons with their standard charge to mass ratios, imagine particles or debris with extreme ratios. Highly charged, extremely light, or both. These particles wouldn't just flow along magnetic field lines. They'd create new pathways. They'd conduct electricity through regions of space that normally act as insulators. They'd turn empty vacuum into something resembling a semiconductor, a material that can conduct under the right conditions, but isn't a straightforward conductor or insulator. The internal brief used a term that's only appeared in obscure plasma physics papers: Lorentz doping. The concept is borrowed from semiconductor engineering, where doping means adding impurities to a material to change its electrical properties. Silicon is a mediocre conductor on its own, but add tiny amounts of phosphorus or boron, and suddenly it can be engineered into transistors and computer chips. Lorentz doping suggests something similar happening in space plasma. Add particles with unusual charge-to-mass ratios to the solar wind and magnetospheric environment, and you change how that environment conducts electricity. You turn interplanetary space from an insulator into a wire. Let me give you an analogy that doesn't require a physics degree. You have a garden hose, and you're spraying water at a sponge. Most of the water gets absorbed. Some of it splashes off, but the sponge does its job. Now, replace the sponge with a metal grate. Same water pressure, completely different result. The water goes straight through. The metal doesn't absorb anything. It just provides a structure for the water to flow through without resistance. That's what the brief suggests is happening between Earth and the Sun. The sponge of normal space, which partially blocks and partially absorbs solar wind, got replaced with a metal grate of highly conductive particles. Same solar wind, completely different interaction. This matters because normal solar wind doesn't cause the kind of sustained effects we're seeing. Solar wind is a constant stream of charged particles, mostly protons and electrons, flowing outward from the sun at a few hundred kilometers per second. Earth's magnetosphere handles this easily. It's been handling it for billions of years. Auroras are the visible evidence that the system works. But if you change the conductivity of the space between the sun and Earth, even minor variations in solar wind suddenly have amplified effects. A small increase in particle density or magnetic field strength, something that would normally cause a brief uptick in auroral activity, instead triggers cascade effects throughout the entire magnetospheric system. The brief mentioned observations from multiple monitoring stations showing correlated fluctuations in solar wind parameters and Earth's magnetic field that shouldn't be possible with the time delays and energy dissipation that normally occur. It's like pressing a doorbell and having every light in the house flicker instantly. The response is too fast and too widespread for normal cause and effect. Something is coupling these systems more efficiently than standard physics predicts. Here's where the speculation gets uncomfortable. Standard comet debris is not conductive. Water ice is an insulator. Silicate dust is an insulator. Even most metals, when dispersed as fine particles in vacuum, don't create continuous conductive pathways. So what kind of material could do this? The brief didn't answer directly, but it referenced particle composition analyses from spacecraft that passed through the debris field. Anomalously high concentrations of ionized metals, unusual isotopic signatures, particle size distributions that don't match typical comet fragmentation patterns. Every measurement pointed toward material that shouldn't exist in a comet's tail. The contrast with normal solar wind is crucial to understand. When the sun is quiet, producing minimal flares and coronal mass ejections, Earth's space weather should be calm. We should see background levels of particle radiation, modest auroral activity at high latitudes, and stable conditions for satellites and communications. Instead, we're seeing variations in Earth's electromagnetic environment that correlate with minor solar wind changes at a ratio of 10 to 1 or more. A 1% increase in solar wind density produces a 10% increase in magnetospheric disturbance. That amplification factor is the signature of a system that's been fundamentally altered. Someone in the scientific community started calling it losing our insulation. The magnetosphere is still there, still providing structure and some degree of protection, but we've lost the insulating properties of the space around Earth. Charged particles that should be deflected or absorbed are finding pathways through. Energy that should be dissipated is being channeled directly into our electromagnetic environment. We didn't lose our armor. We lost the air gap between the armor and our skin. And that might be worse. The brief included a projection that should make anyone who depends on GPS, satellite communications, or electrical power grids extremely nervous. If the debris field continues to exhibit these conductive properties for the projected duration, and if Earth remains embedded in it for months as orbital mechanics suggest, we're looking at a period where minor solar activity produces major terrestrial effects. No massive solar flares required. No dramatic coronal mass ejections necessary. Just the sun's normal breathing, amplified through a conductive medium we didn't know could exist. You have to ask, what kind of object leaves behind material like this? What kind of comet trail contains debris capable of altering electromagnetic interactions across millions of miles of space? The answer from mainstream astronomy is none. Comets don't do this, which means either our understanding of comets is catastrophically incomplete, or 3I Atlas isn't what we thought it was. And if it's not a comet, if it's something else entirely, then every assumption about where it came from and what it represents needs to be reconsidered. Because objects that can dope interplanetary space with conductive material don't just form in the ordinary processes of stellar system evolution. Let's establish what we actually know before we dive into speculation. 3I Atlas is, according to every mainstream astronomical observation, a comet. It has an icy nucleus. It developed a visible coma as it approached the sun. It exhibited a tail pointing away from the sun due to solar radiation pressure. Hubble imaged it. The James Webb Space Telescope analyzed its spectral signature. The Parker Solar Probe collected data during its close approach. Every observation confirmed it had characteristics consistent with a comet, specifically a long-period comet that originated outside our solar system. Typical comet composition is what you'd expect. water ice, carbon dioxide ice, frozen methane, embedded dust particles, trace organic compounds. It's a dirty snowball from deep space, exactly as comets have been described for decades. Now, the twist. The internal brief included composition analyses that described debris with metallic content far exceeding normal comet parameters. Not just trace metals like you'd find in dust grains, but concentrated metallic particles with unusual isotopic ratios. Specifically, the report mentioned enhanced abundances of elements like iron, nickel, silicon, and oxygen in forms that suggest formation under extreme temperature and pressure conditions. This is not typical comet chemistry. This is material that was processed through stellar fusion or something similarly energetic. The James Webb Space Telescope detected unusual gas ratios in 3I Atlas's coma during its active phase. High concentrations of carbon dioxide relative to water, significant amounts of carbon monoxide, organic compounds that didn't quite match the expected profiles from pristine interstellar ice. These observations are real and documented, but their interpretation has been conservative. Scientists said it showed interesting compositional variations. Nobody said it showed signs of stellar processing, until the brief suggested maybe they should have. Polarimetric observations, which measure how light is polarized when it scatters off particles in the coma, showed patterns indicating complex grain structures. Multiple research papers noted this without alarm. Comets have complex grain structures all the time. But if you're looking for evidence of metallic particles mixed with ice, those polarization patterns start looking less like normal comet behavior and more like evidence of contamination. Contamination with material that has no business being in a comet. This is where we need to talk about tidal disruption events, and I promise it connects. A tidal disruption event, or TDE, happens when a star gets too close to a black hole. The black hole's gravity is so intense and varies so sharply with distance that it literally tears the star apart. The near side of the star experiences much stronger gravitational pull than the far side, stretching the star like taffy until it disintegrates. The stellar material, now reduced to a stream of gas and debris, falls into the black hole, often producing brilliant flares of radiation as it's consumed. Tidal disruption events are real, observed phenomena in astrophysics. They're rare, violent, and they scatter stellar material across interstellar space. White dwarfs are the remnants of stars like our Sun after they've exhausted their nuclear fuel. The outer layers blow off, leaving behind a dense core about the size of Earth, but with mass comparable to the Sun. White dwarfs are made of degenerate matter, mostly carbon and oxygen, with a thin hydrogen or helium atmosphere. The material inside is incredibly dense and has been processed through millions of years of fusion reactions. If a white dwarf were torn apart in a tidal disruption event, the debris would be rich in heavy elements, processed through stellar fusion and expelled into space at tremendous velocities. Here's the uncomfortable thought experiment. What if 3I Atlas isn't just a comet? What if it's the aftermath of something catastrophic that happened light years away? What if the icy exterior, the comet-like behavior, is just a disguise accumulated during millennia of travel through cold interstellar space? What if the core material, the debris now threading through our solar system, is stellar shrapnel from a white dwarf that was torn apart by a black hole? This is entirely speculative, but it explains things that standard comet models don't. It explains the unusual metallic content. It explains the isotopic ratios suggesting high temperature formation. It explains why the debris exhibits conductive properties normal comet material shouldn't have. Stellar material processed through fusion contains ionized metals and complex electromagnetic properties. Wrap that in a few meters of accumulated ice from interstellar space, and from a distance, it looks like a comet. But it's not. It's something far stranger and potentially far more dangerous. Chemical fingerprints are how astronomers trace the origins of objects. Different stars produce different isotopic ratios of elements based on their mass, age, and fusion processes. Our Sun has a specific chemical signature. Other stars have different signatures. If you could analyze the isotopes in 3I Atlas's debris in detail, you could theoretically determine what kind of star it came from. The brief mentioned isotopic anomalies, but didn't elaborate. This could mean the data is incomplete, or it could mean the data is so weird that analysts don't know how to interpret it. There's also the timing issue. If 3I Atlas is stellar debris from a tidal disruption event, that event would have occurred centuries or millennia ago, given the distances and travel times involved. The object has been coasting through interstellar space, accumulating ice and dust until it happened to pass through our solar system. We're not seeing the initial catastrophe. We're seeing the delayed consequences. The shrapnel finally reaching a populated area millions of years after the explosion. The brief included one line that didn't fit anywhere else. Consider the possibility of coordinated origin events. This is scientific language for what if there's more than one? If one object from a tidal disruption event ended up on a trajectory through our solar system, others could be on similar paths, separated by decades or centuries. We might not be dealing with a unique encounter. We might be dealing with the first impact from a debris field that will continue arriving for generations. And if the first piece already altered Earth's electromagnetic environment, what happens when the next one arrives? The question you should be asking now is, if there was a catastrophic event that created this debris, did we see it happen? Did telescopes catch the flash when a star was torn apart and sent material in our direction? And if they did, why didn't anyone connect it to 3I Atlas until now? Gamma-ray bursts are the most energetic electromagnetic events in the universe. They release more energy in seconds than our Sun will produce in its entire 10 billion year lifetime. Astronomers detect them as sudden, intense flashes of gamma radiation coming from distant galaxies. The leading theory for long-duration gamma-ray bursts is that they're produced by massive stars collapsing into black holes. Short-duration bursts are thought to come from neutron-star collisions. Both involve catastrophic stellar death, and both scatter stellar material across interstellar space at relativistic speeds. Gamma-ray bursts are real, well-documented, and absolutely terrifying in their power. GRB 250702b was detected on July 2, 2025, by multiple gamma-ray observatories, including NASA's Fermi satellite. The designation follows standard astronomical naming conventions. GRB for gamma-ray burst, followed by the date of detection. It was classified as a long-duration burst, lasting approximately 30 seconds, originating from a region in the constellation Lyra. The distance was estimated at several billion light-years based on redshift measurements. As gamma-ray bursts go, it was notable but not exceptional. Astronomers logged it, studied it, published papers, and moved on. Just another cosmic catastrophe in a universe full of them. Here's where the speculation enters. The internal brief suggested that when you trace back the vector of 3I Atlas's trajectory, accounting for gravitational perturbations from stars it passed along the way, the origin point aligns suspiciously well with the direction of GRB 250702b. Not perfectly. Interstellar trajectories aren't that precise over thousands of light years, but within the margin of error you'd expect given the uncertainties involved. The GRB happened billions of years ago, given the light travel time. The debris would have been traveling since then, finally arriving in our solar system in 2025. Think of it like hearing a gunshot in the distance, and seconds later, feeling the bullet hit. The gamma-ray burst was the muzzle flash. 3I Atlas is the bullet. We saw the flash billions of years after it happened, because light was ahead in the race. The debris arrived later because matter travels slower than light, even when it's moving at a significant fraction of light speed. The timing works if you assume the tidal disruption event that created the gamma ray burst also expelled material in our direction. This creates a narrative that's almost too cinematic to believe. A massive star or white dwarf located billions of light years away in the direction of Lyra experienced a catastrophic event. Maybe it collapsed into a black hole. Maybe it collided with another stellar remnant. The event produced a gamma-ray burst visible across the universe and scattered stellar debris in all directions. One stream of that debris, by pure cosmic chance, was aimed at our solar system. It traveled through interstellar space for billions of years, accumulating ice and dust until it passed through our neighborhood in 2025, looking for all the world like just another comet. The problem with this narrative is verification. We can't prove the connection without detailed isotopic analysis of the debris and theoretical modeling of the tidal disruption event. The brief acknowledged this uncertainty, but argued the circumstantial evidence is strong enough to warrant serious consideration. The trajectory alignment, the unusual composition, the electromagnetic properties that don't match standard comet models. Individually, they're interesting anomalies, but together they form a pattern suggesting something far more exotic than a typical interstellar comet. Here's the conspiracy angle, and I'll present it without endorsing it. Some researchers claim that early trajectory calculations, performed when 3I Atlas was first discovered, showed the alignment with GRB 250702b. They claim this data was quietly reclassified, or at least not publicized, possibly because the implications were too disturbing for public consumption. The idea that we're being hit by stellar shrapnel from a gamma-ray burst event, even one that happened billions of years ago, is the kind of cosmic horror that could trigger widespread panic. So the data was noted internally, never fully disclosed, and most astronomers worked with the simpler explanation: it's just a comet. This is a common pattern in conspiracy narratives. Somebody knew. Somebody saw the connection. The data exists, but was suppressed or ignored. I can't verify these claims, and the brief didn't endorse them explicitly, but it acknowledged the controversy exists within the scientific community. The truth is probably more mundane. Astronomers deal with so much data and so many objects that connecting one small comet to one distant gamma-ray burst would require someone to actively look for the connection. Unless you're already suspecting a link, you'd never notice it in the noise. The dangerous question is, if one object came this way, traveling for billions of years from a catastrophic stellar event, how many others might be on trajectories we haven't calculated yet? Tidal disruption events and gamma-ray bursts don't produce single projectiles. They create debris fields expanding in all directions. We're seeing one piece of that field. Where are the others? How many more bits of stellar shrapnel are coasting through the galaxy, invisible until they happen to pass close enough to a star for sunlight to illuminate them? And how many of those objects will pass through our solar system in the centuries ahead? The brief ended its discussion of the GRB connection with a single sentence. 3I Atlas may not represent a unique encounter, but rather first contact with a class of objects we have not yet learned to identify or track. That's scientific language for there are more of these, and we don't know where they are. The gamma-ray burst wasn't just the gunshot that fired the bullet. It was the artillery barrage, and we've only been hit by the first shell. Jupiter's magnetosphere is a monster. Earth's magnetic field extends roughly 60,000 kilometers into space, which sounds impressive until you compare it to Jupiter. The Jovian magnetosphere extends more than 7 million kilometers toward the Sun and stretches even farther in the opposite direction, creating a magnetic tail that reaches past Saturn's orbit. If you could see magnetic fields with the naked eye, Jupiter would appear larger than the full moon from Earth. It's the largest structure in the solar system created by a single planet, and it's incredibly complex. The physics of Jupiter's magnetic field are well understood. Jupiter rotates once every 10 hours, and its metallic hydrogen interior acts like a massive dynamo, generating a magnetic field 14 times stronger than Earth's at the cloud tops and much stronger near the core. This field traps charged particles from the solar wind and volcanic emissions from Jupiter's moon Io, creating intense radiation belts that would kill an unshielded human in hours. The magnetosphere interacts constantly with the solar wind, producing powerful radio emissions detectable from Earth with relatively simple equipment. Now consider the scenario the internal brief suggested as a thought experiment. If a conductive debris field, something like what 3I Atlas left behind, were to thread through Jupiter's magnetosphere, what would happen? Jupiter doesn't have a solid surface to ground electrical currents like Earth does. The planet is mostly gas and liquid hydrogen. Its magnetosphere is much larger and more energetic than Earth's. If the debris created a conductive pathway through that environment, the effects would be proportional to the system's scale. Earth experienced sustained electromagnetic coupling with minor but growing effects. Jupiter would experience something far more intense. The concern isn't theoretical. 3I Atlas followed a trajectory that passed relatively close to Jupiter before approaching Earth. The debris field it left behind is spread along its orbital path. Jupiter, with its enormous gravitational influence and massive magnetosphere, would have interacted with that debris already, or will interact with it soon, depending on the exact distribution of material. Nobody is actively modeling this scenario because nobody considered it necessary until the Earth effects became undeniable. Jupiter naturally emits strong radio waves generated by interactions between its magnetosphere and the solar wind. Amateur radio enthusiasts can detect these emissions, called decometric radiation, with backyard equipment. Professional observatories monitor Jovian radio emissions constantly because they provide information about conditions in the outer solar system. Any significant disturbance to Jupiter's magnetosphere would show up as anomalies in these radio patterns. Unexpected bursts, unusual frequencies, or changes in emission timing that don't correlate with known solar wind conditions. Some researchers have started quietly reviewing archived radio telescope data from the period when 3I Atlas passed through Jupiter's region of space. The brief mentioned preliminary findings that suggest non-standard emission patterns during that time frame. This is deliberately vague language, probably because the analysts aren't sure what they're seeing. Jupiter's magnetosphere is chaotic under normal circumstances. Distinguishing genuine anomalies from natural variation requires careful statistical analysis and comparison with historical baselines. Here's the terrifying analogy. If Earth was a stress test for this phenomenon, Jupiter is the full-scale load test. Earth's magnetosphere is relatively small and simple. We can monitor it comprehensively with existing satellite networks. We can measure the effects and, hopefully, adapt our technology to cope. Jupiter's magnetosphere is orders of magnitude larger and more powerful. If the debris field creates sustained electromagnetic coupling there, the energy scales involved would be enormous. We might see radio emissions from Jupiter intensify dramatically. We might observe auroral activity on Jupiter that exceeds anything previously recorded. We might even detect effects propagating through the solar system's magnetic environment, influencing other planets and the solar wind itself. The brief posed a question that nobody wants to answer. If the debris field is capable of altering electromagnetic interactions at multiple locations throughout the solar system, does that make our local space environment fundamentally unstable? Solar systems are supposed to be relatively predictable once they reach steady state. Planets orbit, the sun shines, magnetic fields interact in well-understood ways. Introduce a conductive medium threading through the system, and suddenly you have a mechanism for coupling distant regions electromagnetically. Changes in one location could propagate to others faster than normal cause and effect relationships would allow. Real planetary science provides some grounding here. Jupiter's magnetosphere is actively studied by missions like Juno, which has been orbiting Jupiter since 2016 and continues to return data about the planet's magnetic field, radiation environment, and auroral activity. If something genuinely weird were happening at Jupiter right now, Juno would detect it. The problem is that Juno's data takes time to analyze, and the mission's focus is on long-term studies of Jupiter's internal structure and magnetic field evolution. Short-term anomalies might not trigger immediate attention unless someone is specifically looking for them. The risk nobody is modeling is cascade effects. Suppose Jupiter's magnetosphere becomes electromagnetically coupled to the debris field, and that coupling influences the solar wind flow patterns in the outer solar system. Those altered flow patterns could affect Saturn, Uranus, Neptune, and even feed back toward the inner solar system, creating secondary effects at Earth. We're not just dealing with isolated planetary responses to a comet's debris. We're potentially dealing with a system-wide phenomenon where one object's passage creates interconnected disturbances that amplify each other. The brief's language became almost philosophical when discussing Jupiter. We assumed planetary magnetospheres operate in relative isolation, connected only through the solar wind and occasional cosmic ray events. If this assumption is incorrect, if conductive media can create pathways for direct electromagnetic interaction between planetary systems, our models for solar system dynamics require fundamental revision. That's a scientist's way of saying we might not understand how our own solar system works at the level we thought we did. You have to wonder what happens next. Earth is dealing with sustained electromagnetic effects from debris we're still moving through. Jupiter may be experiencing similar or more intense effects from the same debris field, but on a scale that makes Earth's problems look trivial. Other planets along the debris path, Mars, Saturn, any world that passed through this material, they might all be experiencing their own versions of this phenomenon. We're focused on Earth because we live here, but the entire solar system might be responding to what 3I Atlas left behind. And if that's true, if this object fundamentally altered the electromagnetic environment of our solar system, the question becomes, how long does it take to return to normal? And will it ever return to normal? Or is this the new baseline we have to learn to survive in? Something is happening across multiple domains of space science simultaneously, and whether it's directly related to 3I Atlas or part of a broader pattern, the convergence is unsettling. These aren't isolated anomalies that can be explained away with existing models. They're interconnected observations that suggest our understanding of the space environment might be fundamentally incomplete. When multiple independent systems start showing coordinated deviations from expected behavior, you're either witnessing an extraordinary coincidence or you're seeing evidence of something systemic that nobody predicted. Satellite operators have reported unusual drag anomalies over the past several months, and the pattern is becoming impossible to ignore. Satellites in low Earth orbit experience atmospheric drag because Earth's atmosphere doesn't have a sharp boundary. It gradually thins with altitude, but even at orbital heights of 400 to 600 kilometers, enough atmosphere exists to create tiny amounts of drag that slowly pull satellites downward. Operators compensate for this with periodic thruster burns to maintain orbital altitude. The amount of drag depends primarily on solar activity. When the sun is active, increased ultraviolet and X-ray radiation heats Earth's upper atmosphere, causing it to expand upward. More atmosphere at orbital altitudes means more drag. When the sun is quiet, the atmosphere contracts, drag decreases, and satellites maintain their orbits more easily. What's unusual now is that drag variations don't consistently correlate with solar activity levels the way they should. Satellites are experiencing more drag than expected during solar quiet periods, and less drag than expected during active periods. Some satellites show drag spikes that don't correspond to any measurable increase in solar output. Others maintain stable orbits during solar events that should have caused noticeable atmospheric expansion. The pattern makes sense if something is altering how solar energy couples to Earth's upper atmosphere, creating heating that doesn't follow standard models. If the conductive debris field is channeling energy into the atmosphere through pathways our models don't account for, you'd see exactly this kind of decoupling between solar input and atmospheric response. Mission controllers are quietly adjusting their orbital maintenance schedules, burning more fuel than planned in some cases and less in others, trying to compensate for an atmosphere that's behaving unpredictably. These adjustments cost money and shorten satellite lifespans. More concerning, they indicate we can't reliably predict the space environment anymore, even with sophisticated models and real-time solar monitoring. When basic assumptions about how the sun affects Earth's atmosphere stop working, every calculation built on those assumptions becomes suspect. Artificial intelligence-driven plasma modeling has become a major tool in space physics research over the past few years. Traditional physics-based models struggle with the complexity of plasma dynamics, the behavior of ionized gases in electric and magnetic fields. Plasma is the fourth state of matter, distinct from solid, liquid, and gas, and it dominates the space environment. 99% of the visible universe exists in plasma form. The sun is plasma. The solar wind is plasma. Earth's ionosphere contains plasma. Understanding how plasma behaves in complex electromagnetic environments is crucial for space weather prediction, but the mathematics are brutally difficult. Plasma responds to electric and magnetic fields, but it also generates those fields through its motion, creating feedback loops that standard equations can't solve analytically. Modern machine learning approaches can find patterns in massive datasets that human analysts would miss. Feed a neural network thousands of observations of plasma conditions and their outcomes, and it can identify correlations invisible to traditional analysis. Recent AI-driven studies have identified unexpected structure in the space environment, regions of enhanced electromagnetic activity that persist longer than models predict, correlated fluctuations across widely separated locations, and evidence of conductive pathways through regions previously thought to be electromagnetically quiet. These AI findings predate 3I Atlas's arrival by months or even years, but they're consistent with a space environment that has more electromagnetic complexity than our simplified models assumed. The question nobody wants to ask is whether the AI models were detecting something we couldn't see with conventional analysis. Were they finding evidence of conductive structures in interplanetary space before 3I Atlas arrived? Could there have been debris from other objects, earlier encounters we never identified, already altering the electromagnetic environment in subtle ways? Or were the AI models simply overfitting noise, finding patterns that don't really exist because they're trained to find patterns? The uncomfortable truth is we don't know how to evaluate these results yet. We're using tools that work in ways we don't fully understand to study environments we've barely begun to characterize. Astrophysicists have been revising estimates of intermediate mass black hole populations based on better observational data and improved theoretical models. Intermediate mass black holes, with masses between 100 and 100,000 times the Sun's mass, occupy a strange middle ground in the black hole population. They're not massive enough to create the obvious effects of supermassive black holes sitting in galaxy centers, eating stars and producing brilliant quasar emissions. But they're too massive to form through simple stellar collapse, like stellar mass black holes, which form when individual massive stars exhaust their fuel and implode. The formation mechanisms for intermediate mass black holes remain uncertain. They might form through runaway stellar collisions in dense star clusters. They might be primordial, formed in the early universe. Or they might grow through mergers of smaller black holes over cosmic time. New observations suggest these objects might be more common than previously thought, hiding in globular clusters and dwarf galaxies where they're difficult to detect. If intermediate mass black holes are common, that changes the statistics for tidal disruption events. A tidal disruption event requires a star to wander too close to a black hole, and the probability of this happening depends on how many black holes exist and how many stars are orbiting near them. More intermediate mass black holes means more opportunities for stars to get shredded. And if tidal disruption events happen more frequently than old models predicted, the amount of stellar debris scattered through interstellar space could be significantly higher than astronomers assumed. Think about what this means for 3I Atlas. If tidal disruption events are common, then interstellar space might be full of stellar shrapnel, traveling in random directions at various speeds. Most of it would never encounter our solar system. The galaxy is enormous and mostly empty, but over billions of years, occasional pieces would pass through, and we'd have no way to predict when or how often. 3I Atlas might not be unusual. It might be our first recognition of a common phenomenon we never noticed before, because we weren't looking for it or didn't know what signs to look for. The debris looks like a comet from a distance. You need close observation and detailed analysis to recognize it's something stranger. The common thread through these developments is that space isn't empty and it isn't simple. The vacuum of space contains structure that we're only beginning to map comprehensively. Magnetic field lines thread through interplanetary space, connecting the sun to planets and extending far beyond the solar system's visible boundaries. Electric potentials exist between regions of different plasma density and temperature. Particle populations, from solar wind protons to cosmic rays from distant supernovae, stream through this environment continuously. Electromagnetic waves at radio, ultraviolet, and X-ray frequencies propagate outward from the sun and inward from deep space. This structure interacts with planetary magnetic fields, solar wind variations, cosmic rays, and apparently with debris from catastrophic stellar events light years away. We built our understanding of space weather and planetary magnetospheres assuming these structures were relatively stable and predictable over human timescales. The Sun has an 11-year activity cycle. Planets orbit with clockwork precision. Magnetic fields fluctuate, but return to baseline configurations. This assumption of stability allowed us to build models, launch satellites, and construct technology that depends on predictable electromagnetic environments. If that assumption is wrong, if space is more electrically active and interconnected than we thought, if transient phenomena like debris fields can alter electromagnetic coupling across millions of miles for extended periods, then our entire framework for understanding how solar systems work needs updating. Not minor corrections. Fundamental revision. The cultural angle matters too, and it's worth examining why narratives about terrifying cosmic phenomena resonate so strongly with public imagination. Part of it is legitimate concern. We depend on technology that's vulnerable to space weather in ways most people don't think about. GPS doesn't just help you navigate while driving. It provides timing signals that synchronize financial transactions, power grid operations, and telecommunications networks. Lose GPS, and modern infrastructure starts failing in cascading ways. Satellite communications connect remote regions, enable weather forecasting, coordinate disaster response. Power grids are vulnerable to geomagnetically induced currents during severe space weather events. These systems are all susceptible to electromagnetic disturbances, and we've built a civilization that can't function without them. But part of the resonance is something deeper and more primal. We like to think we understand our environment. We like to feel safe. The illusion of comprehension provides comfort even when it's not entirely justified. Discovering that our planet's protective magnetic shield can be compromised by material we didn't know existed, traveling through space for billions of years from an event we can barely comprehend that violates our sense of security at a fundamental level. It reminds us that we live in a universe that doesn't care about our comfort or survival. We're not the main characters in some cosmic narrative. We're just here, on a planet that happens to orbit a star, and sometimes things happen that we have no control over and didn't see coming. The myth-busting is important here, because sensationalism helps nobody. 3I Atlas did not destroy Earth's magnetosphere. The planet still has magnetic protection. The field's strength hasn't collapsed. Satellites aren't falling from the sky en masse. Power grids haven't collapsed into permanent blackout. Civilization isn't ending. What we're experiencing is subtle compared to apocalyptic scenarios depicted in disaster movies, but subtle doesn't mean harmless. Small persistent effects compound over time in ways that are easy to underestimate. A few % increase in satellite failure rates means more frequent and expensive replacements. A modest uptick in GPS inaccuracies affects navigation systems, surveying, and precision agriculture. Slightly higher radiation exposure for astronauts shortens their career durations and increases long-term health risks. Individually, these are manageable problems, but collectively, they represent a new operating environment that our technology wasn't designed for. We're adapting in real time, upgrading systems, revising safety protocols, but adaptation takes time and resources we hadn't budgeted for. The established science versus speculation distinction needs to remain clear, and I've been careful throughout this narrative to mark the boundaries. Mainstream astronomy has not confirmed that 3I Atlas left a conductive debris field that's altering Earth's electromagnetic environment. Official space agencies have not declared a sustained connection event at Earth's magnetopause. The gamma ray burst connection is a hypothesis based on trajectory analysis and compositional anomalies, not a proven fact accepted by the scientific community. What we know for certain is limited. 3I Atlas is an interstellar comet that passed through our solar system in 2025. It has unusual compositional properties based on spectroscopic observations from multiple telescopes, and Earth's space weather has shown anomalies during and after its passage that don't perfectly match standard models. Everything else, the conductive filament theory, the stellar shrapnel hypothesis, the sustained electromagnetic coupling, it's all inference, speculation, and pattern matching that might be revealing deep truths about our cosmic environment, or might be seeing connections that don't exist. But here's the final thought that should lodge itself in your mind, like a splinter you can't quite remove. We have always assumed the sun was a distant furnace, pouring energy into space that our magnetosphere deflects like a shield deflects arrows. We assumed the 93 million miles between Earth and Sun was empty protection, distance, and vacuum that keeps us safe from our star's constant radiation. What if that distance isn't protection? What if it's just space, neutral territory, waiting for a conductor to bridge it? What if the sun has always been a power source, not a threat, and we've been safe only because no switch existed to complete the circuit between source and ground? 3I Atlas might have been that switch. A cosmic accident, a fragment of a star torn apart billions of years ago, traveling through the galaxy until pure chance brought it through our solar system at exactly the right trajectory to leave conductive debris threading between Earth and Sun. We didn't build this connection. We didn't ask for it. We didn't even know it was possible. But now it exists, and we're learning what it means to be plugged into a power grid we never knew we were standing next to. The wait for answers is over. The silence that followed the flyby, the months of uncertainty and speculation, they've ended. The silence is broken, and the message we're receiving is that the universe is far stranger and more electrically alive than we imagined. We're not just passengers on a planet orbiting a star in a mostly empty solar system. We're nodes in an electromagnetic network that spans the solar system and possibly extends beyond, connecting us to stellar processes and cosmic events in ways we never suspected. And we just discovered we're not isolated anymore. The debris field is still threading through our space. We're 40% through, according to the leaked brief. The connection is live, conducting energy from the sun into Earth's magnetosphere through pathways that shouldn't exist but do. And somewhere out there, across the vast darkness between stars, other objects might be traveling toward us, carrying their own electromagnetic signatures, ready to flip switches we didn't know existed. The galaxy is full of catastrophic events: stars exploding, black holes colliding, tidal disruptions scattering stellar material across light years of space. Some of that material is aimed in our direction, coasting through the void, and we won't see it coming until it's already here. The question isn't whether we'll survive this encounter with 3i Atlas. We probably will. Humanity is adaptable, and our technology can be upgraded to handle new electromagnetic conditions if we dedicate resources to the problem. The question is, what do we do when the next one arrives? How do we prepare for a class of cosmic objects we only just learned to recognize? How do we build early warning systems for debris that looks like ordinary comets until detailed analysis reveals their stellar origins? And how do we construct a technological civilization that can thrive in a solar system that's more electromagnetically connected, more alive with invisible currents and fields and conductive pathways than we ever imagined possible? The answers aren't in any textbook yet. This is uncharted territory in the most literal sense. We're writing the manual now, in real time, as we move through stellar shrapnel that traveled billions of years to reach us. Every satellite adjustment, every model revision, every AI-detected anomaly is a data point in a new understanding of how solar systems actually work when you account for factors nobody thought to include before. Welcome to the new normal. Space isn't empty, it's structured, threaded with fields and currents and debris from cosmic catastrophes we can barely imagine. It's wired in ways we're only beginning to detect. And we're all connected now, whether we wanted to be or not. The universe flipped a switch we didn't install, and now we get to discover what happens when a planet becomes part of a circuit it never asked to join. The adventure, if you can call it that, is just beginning.